Everyone. Welcome to the first evening seminar in the series. So it's a great pleasure this week to introduce a former colleague at a college in London, Tamer Zaki, and Tamer is going to tell us all about seeing in the dark. Over to you, Tamer.
Thank you, Phil, for the invitation. It's my pleasure to join you from Johns Hopkins to share this the work that we've been doing on data assimilation, and the title of the talk is Seeing in the Dark. This work was done by three members of the group, mostly Mangza and Chi. We're students. Chi now has moved on to become a faculty member in San Diego, and David Bokta, who's a postdoc in the group. And of course, it's had input from many other members of the group and collaborations. The idea of seeing in the dark is that observations are often limited. I started my research in the field of transition, and at the time, a significant problem was transition in high-speed flows. And this is an example of an image from Colombia that is taken by infrared camera, and you could see that you can get a heating pattern on the space shuttle. And this is a very limited set of data that you could get of the space shuttle. And the idea is you're trying to interpret the flight environment around the space shuttle. This is not just a unique example of having limited data and uncertainty in the environment. In fact, this happens quite often. And the trick is to be able to interpret the data. So if you look at these thermal images, then you could see that there's significant heating here, and that gives you a sense that, okay, the flow is laminar in this region, and then transition to turbulence. And this interpretation is based on direct observation of the data, but what we'll try to do today is discover the environments that actually generated this heating. And if you look as far back as the early shuttle experiments, there's all these reports about how do you interpret the data, and this idea goes back even longer from numerical weather prediction, where you have very limited observations and you try to interpret them. It's not just about the space shuttle. Even in high-speed flows, even if you go to the lab, this is an example from an experiment at the Air Force Research Lab, where you have a cone in a high-speed Ludwig tube, and this is a high Mach number. And what you might get from the experiment are just a few pressure traces along the cone. And this could be the only thing you get out of the experimental measurements. And then given, perhaps you get some slurring as well. And then given these measurements, you try to understand what the flow looks like. Of course, the interpretation of the measurement could be as simple as saying, well, I see an organized signal here and a turbulent signal here. So transition happens somewhere between these two sensors. And if you have enough sensors, you can interpret it. But there's another perspective, and that's the one that folks from numerical weather predictions adopt. And that's that the signal is actually an encoding of the events that happened in the flow earlier. And if you can decode the signal, you can discover what takes place. And we've actually done this for the example that I'm showing here, where we can try to predict the environmental disturbances in the tunnel that we don't know. And once we have an estimate for them, we can predict the flow over the cone geometry and obtain model observation, compare them to the experiment, and continue to iteratively improve our estimate of the free stream condition until we can reproduce the measurements. Once we do, we have confidence that we're not just reproducing the measurements in our simulations, but we're in fact discovering the entire flow field. So that's the basic idea. Now you could see in applications in high-speed flows and in other areas, numerical weather prediction, environmental monitoring, interpretation of measurements and experiments. Why is this problem challenging, though? If it has such high impact, where does the challenge come from? Well, the problem is challenging because it's an inverse problem, and you're trying to find the state of nonlinear field equations from limited observations. And if the system is chaotic, any deviation from the true state will amplify exponentially. We know that. That's the butterfly effect that we all know very well. How do you eliminate uncertainties? And how do you ensure that your solutions are unique? So I'll give you a very basic example, and that's the Lorentz system. Here we're showing a Lorentz system, which is in Fourier space described by three states. X, Y, and Z. These are, you can think of them as Fourier coefficients of the temperature and the stream function. And if you start from some true initial condition, you are going to follow a trajectory. And we will observe one variable along this trajectory. We observe Y along the trajectory, and our observations are those blue dots. This idea of chaos that we're very familiar with is that if I start, instead of starting at the initial condition, I only slightly perturb it, you could see that the trajectories diverge between the true, which are the gray trajectories, and red, my estimates of the trajectory. So I cannot reproduce the measurements. You can see the trajectory, if the red is not overlying the gray curve, that means we deviate in forward time. But when you're solving inverse problems, it's not just about being very good at predicting the initial conditions so you can reproduce the observation and trajectory. There's a lot more. In fact, in this case, we nearly reproduce all the observations and latch onto the trajectory for a very long time. But if you look at the initial starting point of our estimate, this is the truth here, and this is our estimated initial condition from solving the inverse problem. They're actually quite far. But even though you're far, you're reproducing the observations. And this is the dual butterfly effect. This here says that if you have small changes in the observations, and even though you're reproducing the trajectory for some time, you might go back to different initial conditions. So the solution is not unique even in the simple problem. Another example that we worked on is scalar dispersion. If you have a plume or a source of a scalar in a turbulent field, that scalar will disperse. And if you have a sensor downstream, that sensor will get a highly intermittent signal. And if you only know the sensor signal, can you predict the location of the source? Well, your intuition tells you that this problem is very ill-conditioned. In fact, if this were a laminar flow, you don't know whether the source is nearby and weak or far away and strong for a simple advection diffusion equation if it were laminar. In fact, here turbulence is what introduces some sort of difference between the different source locations. And to show you this visually, I've done an experiment here, computational experiment, where we have a fixed sensor location, and I put 3 sources further away from the sensor and change their intensity. And you'll see the plume in this figure here, and you'll see a time trace of the sensor in this panel. So you could see the time trace of the three experiments look almost identical. And that tells you that it's very difficult to find the true solution, because even small changes in the sensor signal can be due to significant changes in the prediction of the sensor location. However, if you are able to solve this inverse problem, it really opens up a lot of opportunities in terms of understanding turbulent flows, and also to think about new enriching problems, such as how do you optimally place sensors? In this scalar problem, it turns out, well, the optimal placement of the sensor is at the edge of a plume. And if you're trying to differentiate different sources, you want to be at the edge of the plume, not immediately behind. You're not trying to maximize the sensor signal. You're trying to basically identify the edge of the plume, because that gives you a sense of how far the source is. But there are mathematical ways to be able to work on optimal sensor placement and optimal sensor weighting. If you have a network of sensors, how do you preferentially favor certain one versus others? If you have scalar and velocity gradient, how do you weigh those two different quantities? So it's a really rich area. Today, the focus will be on shear flows or wall-bounded flows in turbulence. So our basic question would be, what is the minimum resolution in the lab to be able to reconstruct all the missing scales? If I'm going to do PIV, for example, of course, today we're going to generate our data from a simulation, but if I were to do a PIV and get these flickering light, what is the minimum spatiotemporal resolution for which I can reconstruct all the missing information? And we're not interested in estimation of the information that is just instantaneous. We're interested in, one, a solution to the Navier-Stokes, 2, that can give me a trajectory that actually follows the experimental trajectory, the flow in the experiment, that trajectory as long as possible. So that's a very challenging task. We cannot just use simple interpolation, for example, or an stochastic estimation. We actually have to find a Navier-Stokes solution that can reproduce these trajectories. And then, of course, if we can answer this question, we can start playing games and ask, well, if I only have the outer flow, which experimentally we can measure without having to get so close to the wall, can I reconstruct the missing wall layer, which is very difficult and challenging to visual or probe experimentally? And if I only have wall measurements, for example, that's what happens in engineering application, how far from the wall can I predict turbulence? And we start also discussing ideas about, if I have a single measurement, what is the domain of dependence of that measurement? What does it tell us about the nature of this inverse problem? And the approach we'll adopt is adjoint variational data assimilation. Folks from weather prediction will call this 4D VAR. And we'll first focus on turbulence reconstruction and then the idea of the sensor domain of dependence. So we will first perform a numerical experiment and get surrogate observations. So our reference flow, that would be the experiment, we're going to call U superscript R. So whenever you see capital R, that means that's the reference state, that's the truth that will be hidden from us. And the truth satisfies the Navier-Stokes equations. And it's a channel flow configuration. And from this, we will extract some observations. So cal M here, or script M, will be our measurement kernel. That's how we extract observation from the true state. And we'll extract these observations as a function of time. So as we perform this reference calculation, we're extracting observations at probe locations. And you can see this is ultimately the image that we have. And the idea is, can we see in between these flickering lights? So the procedure is the following. I'm going to have, once I've performed the experiment, I'm going to construct a numerical model of the flow. This model could be LES, it could be one-way Navier-Stokes, it could be PSE if you're interested in transition. For the purposes of today's talk, we're going to use Navier-Stokes. Our forward model is going to be called N for nonlinear Navier-Stokes equations. And if I have an initial condition for channel flow, I can predict its entire evolution. Unfortunately, we don't know the full initial condition. This here is the control vector that we're trying to discover to be able to reproduce the measurements. However, given an estimate of U0, I can solve Navier-Stokes and I can collect model observations and I can compare them to the measurement. And I will define a cost function, which is the difference between my prediction of the measurements or of the observations and the true observations. So my cost function is the true norm of this difference or this error term between my ability to reproduce the observations and the true observations. The key, of course, to this minimization is to find the gradient of the cost function. And there are many different ways to do this. In our group, we've used adjoint methods, and that's what we'll do today. We've also used ensemble techniques and machine learning. So we have papers in all three areas, and we're currently doing a systematic comparison of the performance of the three. So the idea of adjoint variational methods is that given an estimate of the forward field of the initial condition, I can solve Navier-Stokes and collect my model observations. I can compare them to the true observations here and find the errors in my reproduction of these measurements. And that's E sub n. And I also have to store the forward velocity evolution. And we'll see why. Once I get to the end of the time horizon that I'm assimilating information, I solve the adjoint equation. So these are the dual to the Navier-Stokes equations. And you can see the adjoint will be marked by a star. And you can see also that the Navier-Stokes equation, adjoint Navier-Stokes, on the right-hand side is forced by the disparity between our prediction of the measurements and the true measurements. So this disparity is what drives the adjoint equations in backward time. And at the end of adjoint marching, what we have is the gradient of the cost function. Once I know the direction of the gradient, how the cost function increases, I can move in the opposite direction and attempt to reduce the cost function. And we do this iteratively. The other reason for storing, or the reason for storing the forward flow field is because the adjoint equation depends on the forward flow field. So you have to store the forward evolution during your assimilation time window, and you use it in the adjoint system. So I'll show you results now from this procedure for turbulent channel flow. The first example is from RE-tau 180, and we perform DNS. This here is the DNS resolution on the top row, and below it is the resolution of the first set of observation we'll look at. So as a first step, we said, imagine we cannot perform measurements at full resolution of DNS. We can only perform measurements that sample every roughly 8 times the DNS resolution. So delta X of the observation and Y and Z is 8 times what you would need for DNS. And in time as well, we're subsampled. Our assimilation time horizon in this case is 50 plus units. And the first result that I want to show you is just visual, qualitative. And basically this here is the hidden truth calculation. And below it is a reconstruction of the initial condition when the resolution is 1/8 in space and time. So 1/8 cube is over 1/4000, the true resolution. And if you play the 2 videos, you could see that our ability to reproduce the reference flow. I will show this again. You can see our prediction of the initial condition. That's the objective or the control vector that we're trying to assimilate. Our prediction seems reasonable. It has some high frequency noise, but as it evolves, it improves and latches onto the true trajectory and reproduces the experimental measurements. We can quantify the error. We can integrate the error in the horizontal plane and plot it versus wall normal coordinate. And this here is the error in the U component of the velocity as a function of distance from the wall at the initial time. So this is the error in the initial condition that we predicted, and this is in the V velocity. And as we march this predicted initial condition forward, you could see that the error decays. It doesn't diverge as you would expect from the fact that the flow is chaotic. In fact, the error decays. And there's an obvious question, why does the error decay? So we can plot the integrated error. I integrate the error in Y and plot it versus time, and you can see indeed it's decaying in time. Well, the reason the error is decaying is because this forward adjoint loop is targeting the observations, minimize the error in the observation. But which errors are most important in this loop? When you solve the adjoint equation, it is forced by the discrepancy between the true measurements and the model reproduction of these measurements. At the final time, the errors have an entire time horizon to amplify within the adjoint. But the errors at early times have a smaller duration being advanced by the adjoint. So if you think about this idea of dual chaos, or the chaos of the adjoint equations, or the Lyapunov exponent of the adjoint equation, you realize that the latest errors are the ones that have the longest time in the adjoint equation to amplify by the Lyapunov exponent. And the target of this forward adjoint loop is to find the initial condition that reproduces the measurements, but it's really targeting the latest measurements. So if you wanted to have your error be almost uniform in time, you can weigh the measurements and maybe have a decaying weight to say, actually, I want to also be able to reproduce early measurements accurately, and we've done that. But now what happens if I stop having data? I no longer have observations. How good is the state that I predicted? I'm saying here that it has less than 1% error from the true flow. Well, let me continue to march this forward without additional data. So if at this point, you see the colored region was the assimilation window, if I stop having data, my prediction will start to diverge from the true flow. If I get another injection of errors, and this is the shaded region here at 2t, twice the assimilation window, I can perform this data assimilation procedure, and I can ensure that my error again decay. If I stop having data to assimilate, I will start to diverge. So we do this translating window procedure to continue to have accurate data over a long time horizon. These are predictions of velocities. The accuracy of predicting the velocity field. Predicting the gradient is more challenging. So here I'm showing a visual example of vertical structures. To the left, these are the vertical structure lambda2 criteria in the channel. And to the right, I am showing what you would obtain if you simply used the observations and interpolated between them and computed lambda2 criteria. So you can see that the observations are really coarse-grained. You don't predict the gradients accurately. You don't predict vertical structures accurately. But if you were to perform the data assimilation procedure, you get a richer picture. Again, it's noisy because we have all these high-frequency errors in the initial conditions. But as we march our predicted initial condition, you can see that we're capturing these vertical structures. How sensitive is our prediction to noise? If the measurements have some white noise, how well can we reconstruct the flow field? So here I'm looking at the errors in our prediction of span-wise vorticity. And if I add noise to the data, 0% noise, that means I have perfect data that come from the reference calculation, and our error in the vorticity is this lowest gray line. And if I systematically add noise to the measurements, we added 5%, 10% noise, and you could see it's this line here. We're still less than 5% error. So the error in the vorticity field is lower than the noise level we added to the measurement. This here is the error in your prediction if you use just simple interpolation. So you can see you have 40% error in vorticity if you just use the original observations and interpolate. So now we start thinking about, we can do this reconstruction, but what are the limitations? We only took 1/8 of the DNS resolution for our observation. What if I keep coarsening systematically the observation? What is the length scale that matters in our ability to reconstruct the flow? So we systematically change the distance between span-wise measurement locations. And of course, at ZM is my measurement location. At ZM, if I compare my prediction and the true flow, they're very accurate because I have data on this plane. And we can see that because in color, I plotted the true flow, and with the lines, I plotted our estimation of this hidden truth. When the lines and the colors overlap, that means we've done a good job. If I move away in the span from a measurement location and look at how well we predict the flow, now you can start to see that the lines and the colors are not aligned. It means our predictions are not matching the true flow. And we systematically change the distance between span-wise measurement stations and check how well does the error look. So here we're plotting the actual errors, and this here is the distance between two span-wise locations. So if we're only measuring every 112 plus units in the span, or 56 or 28 or 14. So we're progressively bringing the measurement station closer together. And you can see when they're far apart, the error, of course, is lowest at the measurement location, increases, and then decays again. And here, this is very large error. This is 140% error. But of course, as you bring them closer, your error drops. We're down now to 2% errors. And it's homogeneous because the stations are close together. But what is the critical resolution? Well, we can plot a correlation between the true flow and our prediction. So this is the lower correlation here. At the measurement station, the true flow and our prediction are perfectly correlated. And as I increase my distance from the measurement station, the correlation, of course, decays. My prediction of the true flow becomes poor as I move away from the measurement station. This figure, of course, reminds us of the two-point correlation, but they're not exactly the same. Remember, in the two-point correlation in turbulence, we take a reference point and move another point away from it and see where the flow decorrelates. But the point of plotting these two together is to tell you that even though the turbulent structures, for example, at y plus 17, even though the turbulent structures have entirely decorrelated by 28 plus units, the correlation is 0. My reconstruction of the flow 28 units away from the measurement station still is correlated with the true flow by 50% correlation. Again, if you go to higher up at y plus equal 51, the flow decorrelates by 56 plus units. But if I'm 56 plus units from the measurement station, I have 50% correlation between my prediction and the truth. So once you look at the correlation, it tells you, okay, you can from here get a length scale. And this length scale is a Taylor microscale that tells us basically how good the decay rate of your correlation. And you can see here, this is our Taylor microscale versus height. And this curve is the Taylor microscale. And this here is the microscale that we define that say, if your spacing between measurements is smaller than this lambda c, you can reconstruct the flow accurately. And you can see that there are similar values. So the argument here is that if the measurement station are within a Taylor microscale, you can accurately reconstruct the missing information. And by accurately reconstruct them, we're not just using a correlation, we're looking at the flow being correlated with the true state above 90%. How about in the streamwise direction? Now we have advection added to the problem. We first looked at the span because there's no advection in the spanwise direction. In the streamwise direction, you can play games with space and time. So here we're looking at the wall normal coordinates, and this is streamwise coordinate. And these are measurement station in the streamwise direction at 0, delta x of the measurement is delta x, and twice delta x of the measurement, and 3 times. And we're plotting the errors at the initial time in our prediction. And you can see the errors are lowest at the measurement station, which is not surprising. We have information there. And the error increases away from the measurement station. But what I want to alert you to is this region of small error that you see here. Our initial condition has a region of small error here because as this initial condition advances in time, it will land at a probe downstream later in time. And when it does, we have data to compare to. So this more accurate region is because later in time at a downstream location, it will coincide with a measurement. So I have information that we trace back to an initial condition. So if I play, I want you to notice this video has this patch and also these patches here that will become progressively more blue, which means more accurate as they approach the measurement station. So you could see there are these regions of higher accuracy that either start at a measurement station or start in the bulk because they will land on a probe later in time. And over time, we have a more accurate solution. You can do a space-time diagram if you pick a line here at certain height and plot x versus t, and you can see what I was describing. Here, for example, the accurate region is starting from a measurement location, and we labeled them A. B are locations where the accuracy starts in the bulk away from measurement station because later in time, it will coincide with a cross, which is a measurement point. So now we have the space and time, and there's an advection velocity. So we'll construct a new criteria. So we'll start from our old criteria was that your measurement in X have to be within 2 Taylor microscales. The stations, each station gets a Taylor microscale attached to it. So the separation is twice the Taylor microscale. And for time, I say, well, if I satisfy the spatial locations, I just need to make sure that the time resolution of my measurement doesn't violate Lyapunov timescale. If I only get measurements every very long time, a measurement today, another one tomorrow, I can't get accurate predictions because basically chaos, you cannot make predictions in time unless you have data at a resolution that's less than the Taylor microscale. And now we play that game by replacing space and time using an advection velocity. And well, actually, before we do that, so if this here is my region in time that I can do accurate prediction up to Lyapunov timescale and the region in space up to the Taylor microscale, I can reconstruct the flow in when the spatial temporal resolution of the measurement in this region, and all these circles are cases that we have attempted and successfully we're able to predict the flow with correlation coefficients above 90%. Now let's swap space and time by using an advection velocity. I can divide this first criteria by the advection velocity and multiply this one by an advection velocity. And you can see that if I have a higher temporal resolution, which means delta t of the measurement is smaller, I can have a longer spatial separation of the measurements and still accurately reconstruct it. And we verified all these points using data assimilation. Now, what happens if I'm outside? Those are cases where we attempt to do a reconstruction and we couldn't because we don't satisfy the criteria for accurate reconstruction. So now we have a sense that there's two scales that matter, a Taylor microscale and the Lyapunov timescale. Now imagine if you have an entire layer that is missing. So this here, anybody that works in LES is used to the idea of wall modeling. If you're an experimentalist, you might be able to get measurements in the bulk, but not be able to reconstruct the near wall region. And the question is, if I have the measurements inside the bulk, can I predict the flow in this grade region, which in this particular example has a y plus of about 90. And this here is the true flow. And if you use a simple linear stochastic estimator, so you construct a linear stochastic estimator of this problem, you can make predictions that are shown here at two heights halfway through the gray region and at the wall stress. And you can plot the correlation between the estimated field and the true field. And this is what you get. Just a comment, to construct the linear stochastic estimator, you need to be able to get statistics of the flow, like 2-point correlations of the flow. And if you cannot get the measurements, it's difficult to get those statistics unless you can do a simulation. Okay, now if we use adjoint variational methods, I would just flip back and forth. You can see how much richer our prediction is with the data assimilation procedure compared to the linear stochastic estimator. But I must say, we use our linear stochastic estimator as the first guess. So we would not have been successful without it, or at least as successful. It would have been much more difficult to get this result. It would have required a lot more iterations. And if you look at our prediction, the correlation between the predicted flow and the true flow, now at y plus is equal to 45, we've gone from approximately 40% to maybe 70. And we have a better prediction of the stresses near the wall. And again, vertical structures in that layer that was missing, the true state is to the left, and the linear stochastic estimation gives you the figure to the right. And if you use our adjoint approach, you have a much richer interpretation of what happens in that layer. So with this, we had some confidence that the methods are working. And then we went to the biggest challenge, and that's just starting from wall observations only. There's nothing else. We only have information here at this red line, and the channel is entirely dark. How far from the wall can we actually predict the flow? So now we have to change our cost function. It's now the stress at the wall. That's the information that we have. And we try to reconstruct the flow. So this is the true state, and this is our estimation. And you can see here, we're very close to the wall at y plus is equal to 15. We can reproduce the true flow. And our correlation coefficient with the truth is close to 1 at y plus is equal to less than 10 at by 15. We're maybe at 90%. And you can see there are many curves here. These are Reynolds number from 100 to 590. So we've done this exercise for many Reynolds numbers. And then we move up from y plus 15, to y plus is equal to 100. This point, you see the correlation has dropped down to about 60%. We're still getting some of the larger scale motions, but the finer scales are more difficult to identify. And then we go even higher. This is y plus of 300. And then we're basically only predicting the large scale motions. We're not predicting anything else. How well is our prediction near the wall? We look at the true state and the estimated state, and we have interest in strong ejections and sweeps that happen near the wall and the associated high stresses and low stresses at the wall. We've written a paper with Greg on the Lagrangian stochastic vorticity, behavior of vorticity, or Lagrangian stochastic Cauchy invariance for vorticity about these events. And you can see the true is in black and our reconstruction is in gray. and the vortex line are perfectly reconstructed. And if you're interested in the outer large scale structures, this figure has these outer structures from the reference state and their reconstruction. So you can see we do much better in the near wall region, but the accuracy deteriorates with height. I think that was clear in the correlation, especially when you're trying to cross the buffer layer, the accuracy deteriorates very quickly. So what determines how well you can reconstruct the turbulence from wall observation? Every measurement, what's the domain of dependence of that measurement? How does it affect the cost function? What is the shape of that cost function? So all these questions are the focus of the second half of the talk. So this here is an example of a cost function. This one comes actually from the Lorentz system because it's has small dimensions. It's only 3. So we can plot the cost function as a function and its dependence on 2 of the variables, for example. And that's the shape of the cost function of the Lorentz system. And the cost function depends on your measurement. So if we change the quantity that we're measuring, the cost function shape will change. If I weigh the measurements, the cost function will change. And you want to have a sense of what the cost function shape looks like. You can see it's a treacherous landscape and it's full of local minimum and maximum. If you change your measurements or if you weigh them, you can change the shape of the cost function. This here is an example where we weighed the measurements to be able to favor ones that give you a smoother landscape. But before you do any of this, you first have to understand what is a measurement kernel in code, or what is the domain of a dependence of an isolated measurement before you get a sense of what the cost function looks like. So the second half of the talk will focus on this landscape of the cost function. So if we think about this wall measurements and how we can interpret the flow field, we're measuring here, the cost function is a measurement of the shear stress at the wall, so du dy, that I am predicting from my initial condition, estimated initial condition, versus the truth. And if these are far apart, then the cost function would be large and we're trying to drive it to 0. So the convergence depends on the landscape of this cost function. And we want to understand that landscape, but where should we try to understand the landscape? If I put initial condition anywhere, it's really not necessarily a clear indication. Your choice of initial condition could be arbitrary, so it's not a clear indication of what the landscape looks like. It gives you the landscape only at that location, and my initial guess and yours might be different. So it's instructive actually to look at the shape of the cost function at optimality. If let's say you're so good that you're approaching the optimal, or you're even right there, what is the shape of the cost function there? This also simplifies the problem because at optimality, the gradient of the cost function is 0, and the only thing we care about is the Hessian of the curvature of the cost function. And if you have a cost function which is essentially flat, that means your Hessian has practically no curvature and it's very difficult to invert, and you won't be able to necessarily identify the optimal. The system is very ill conditioned near the optimal. And if you have high curvature, that means you have strong sensitivity near the optimal, and your adjoint variational algorithm will drive you towards the optimal. So it's really the Hessian that we're going to look at and try to look at the eigenspectrum of the Hessian. The Hessian is a matrix, and its eigenspectrum tells us the direction that your adjoint optimization would try to basically reconstruct as efficiently as possible. Where you have high curvature, your adjoint optimization is going to try to drive the adjoint looping procedure to minimize the errors by moving in those directions with high certainty. So because we're going to look at the location of the optimal, this really simplifies the problem in very nice ways. I can, instead of looking at my estimation minus the truth, I can define a perturbation U prime, which is the difference between those two. And I call it a perturbation or error or perturbation because we are at the optimal. I can linearize the equation around the optimal. And I can find that U prime, the deviation from this reference flow, is governed by the linearized Navier-Stokes equations. So if I start with an initial perturbation, I can ask myself, how does it evolve? And it follows the linearized Navier-Stokes equation. So this perturbation here will evolve according to the linearized Navier-Stokes and tells me how the cost function is going to change. Note that the forward Navier-Stokes still, even if it's linearized, it still has the true forward flow, which is a fully turbulent channel flow and chaotic. So we haven't thrown out chaos. If you look at the evolution of U prime here, in this video, we start with U prime, which is random noise, and you can see it evolves. We are multiplying it by e to the minus lambda t, and lambda is a Lyapunov exponent. So to keep it order 1, we're multiplying it by this decaying exponential, because in reality, its energy is growing like twice the e to the 2 Lyapunov exponents times time. So chaos is still there. This U prime is still chaotic. So your forward butterfly is still there, here in linearized form. And then if I have a perturbation, I can compute how the cost function changes. We know the gradient is 0. I can compute the Hessian by taking successive perturbations and compute the Hessian of the cost function. So in reality, if I want to figure out how the cost function changes, what I would do is I will take a perturbation to that true state, and I solve Navier-Stokes as I just showed you, the linearized Navier-Stokes, and then I will extract measurement from the outcome. The outcome is U prime, and I take a measurement, and that gives me du prime dy. This is a very expensive process. For every initial perturbation, possible initial perturbation, you have to solve the linearized Navier-Stokes and take measurements. This procedure would be very costly. You have to perturb U, V, and W, and pressure at nx by ny by nz points to be able to compute the Hessian of the cost function. Or you can recognize that you just can take the adjoint. So you move A from here to the left-hand side of the bracket. So now we have an adjoint equation, adjoint linearized Navier-Stokes, acting on the measurement kernel. So this here is the measurement kernel. This is the shear stress computation, the ddy at a point. And the adjoint field that comes from that is U star. Once you have this adjoint field, so we start with the measurement kernel, mu, and we solve the adjoint equation, A times mu, that gives me U star. This here, this adjoint field, you can compute it once, and any initial perturbation that you can dream up, you take this dot product. Only have to compute a dot product, and you can find the cost function, or du prime dy, which is your cost function. So the adjoint field is really the domain of dependence. The adjoint field starting from this kernel is the domain of dependence of your measurement. What's beautiful about it is we've computed it for different Reynolds number for shear stress measurement at the wall, and we compute this adjoint field at different backward times, and you can see it's spreading and growing. It looks like a spot, a turbulent spot. Those of you that worked in transition would know this, that is spreading in backward time upstream. So this measurement was affected by a small region earlier in time, a bigger region upstream earlier in time, and even further, it's a bigger region. And if you compare different Reynolds number, you can see the similarity between the adjoint fields in plus units. So the plus scaling, viscous scaling still works in the adjoint field. You can compare the adjoint field due to measuring streamwise stress, spanwise stress, or pressure at the wall. And you can see that, for example, the streamwise stress, this is the U adjoint field. So if I have a positive U perturbation here, it will have a positive impact onto the streamwise shear stress. But here you can see the spanwise shear stress, a positive U perturbation or a negative U perturbation on the other side of the sensor will both have the same spanwise shear stress at the measurement location and measurement time. And you can see the adjoint pressure is larger, which is consistent with our view of the pressure being non-local. So you can see the domain of dependence of the pressure sensor is larger than that of spanwise or streamwise shear stress. So how do we get to the Hessian from here? Well, now I can rewrite my cost function in terms of this expression that we just derived, the adjoint field times any initial condition. So now I can take the gradient and the Hessian of the cost function with respect to U naught, the initial condition, directly. The dependence of the cost function on the initial condition, I don't need to do forward calculations and take measurements and do, figure out how the cost function that depends on the final state is sensitive to an initial condition through all these forward calculations, I can now directly take the derivative with respect to the initial condition, and you can take it twice, and you can find that the Hessian is actually the cross correlation of the adjoint field. So it's this matrix, which is U star, U star. People also in control theory will call this the observability gramian. So I can compute it since the wall is homogeneous in the streamwise and the spanwise direction. I can do this kernel calculation at different positions along the wall, and I can ensemble average them, and I can find the ensemble average Hessian, and that would be U star bar. And because also of homogeneity, I can take advantage of Fourier transform, and I can write it in terms of every kx and kz wave number. And in Fourier space, it will just be a multiplication of, instead of a convolution of U star, U star. So now I can construct this Hessian, and I can look at how the shape of the cost function look like for every kx, kz that we're trying to optimize in the initial condition. So we do this for measurement horizon, which is 4+ units. So if you only have a measurement and you only want to predict what happened 4 time units earlier, I can plot the eigenvalues of the Hessian as a function of kx plus and kz plus. So for every wave number pair, I can say, how well can I reconstruct the initial condition for a given wave number, kx plus, kz plus, 4 time units earlier. And for every kx and kz, there's an entire spectrum of eigenvalues, but we only look at the leading ones. Those are the main directions that our adjoint optimization is going to try to reconstruct. And you can see that the peak of the spectrum is at kx of 0.12 and kz of 0. And you can see there's another peak coming in, which is streamwise aligned modes. These are spanwise rolls here. These rolls are large. They don't look like anything we often see in turbulence. And you could see that basically what this tells us is that short times, if you only have a measurement horizon of 4 units, the dynamics of turbulence don't have enough time to act. And your measurements are most sensitive to something which you might think is unrealizable in a naturally turbulent environment, which is this big streamwise rolls that you might not see, or if they exist, they'll be very weak. But you can see that there is here a budding sensitivity to elongated near wall structures. Also, I want to point to the fact that here there are 2 sets of contours, there are color and lines, because we've repeated this for different Reynolds numbers, and you can see 180 and 590 match in terms of the contours and also in terms of the mode shape. So the mode shapes, you can interpret them as the directions where you have a steep Hessian, and the adjoint data assimilation is going to try to reconstruct these modes as efficiently as possible. What happens if I have a longer time horizon? We expect that the sensor will be more sensitive or more attuned to the dynamics. So you can see here, this is T plus is equal 4, 8, and 20. And you can see that this peak, there are 3 points that we mark here, 1A and 1B, those are 2 peaks, and region 2 here. And you can see as time increases, that peak that was 1B starts moving inwards, and 1A also moves inward to lower wave numbers. 1B is essentially near wall elongated structures. And the sensor now is sensitive to the dynamics of near wall structures, because over this time horizon, they have an opportunity to amplify and affect the sensor. So if you want to perturb the flow for short time horizon and get an impact on the sensor, these are the type of perturbations. But if you have longer time horizons, these are the types of perturbations that affect your data assimilation. I also want to point out that modes 1A and 1B in every single case are decaying away from the wall. And this tells us that you can reconstruct what happens near the wall, but it's very difficult to reconstruct what happens away from the wall. So if you think about mode 1B, for example, these are near wall structures that extend up to maybe the buffer layer. Y plus here is about 30, but above that, we don't have any sensitivity to what happens above the buffer layer. And if you recall, starting from wall measurements, we were able to reconstruct the flow up to the buffer layer, but then the correlation decayed. The correlation is not zero, and that's because of mode 2 here that I point out. There are some Hessian eigenfunctions that have finite sensitivity in the bulk of the channel, and that's mode 2 that we've marked here. We can explore this further. We can compute the Hessian projected onto the eigenspectrum projected onto POD modes, and we've done that here. If you ask yourself, what if the initial perturbation to the flow was aligned with the POD direction? So I took my initial perturbations to be alpha times a POD mode or the leading POD mode. And if you do that, you can construct a Hessian due to that projection onto the first POD mode. And we've done that. And we're computing it here again for short time and for longer time. The lines are the old Hessian eigenspectrum, and the colors are the new Hessian, which is projected. And with the not aligned, it tells you that at short time, you're not doing very well reconstructing those POD, energetic POD mode, because the energetic POD modes require a certain time scale for them to be able to amplify. And in the data assimilation, you need a certain time horizon to be able to have some sensitivity to that in your reconstruction procedure. But if you take t plus of 20, you can see that now the leading POD modes coincide with the sensor sensitivity. Okay, so I'm going to now just jump ahead. This here is just a figure to remind you that the shape of these modes tells us something about how well we can reconstruct near the wall and away from the wall. Now I want to just jump ahead and for a couple of minutes talk about what happens at even longer times. So beyond t plus of 16, we ultimately, for long enough time, you're going to get adjoint chaos. So for people from transition, this is very close to home. These are spots propagating upstream in backward time, and they look like turbulent spots. And if you wait even longer, the adjoint field forgets its initial condition and just becomes a chaotic adjoint field. So we can compare the chaos of the forward system. This is the forward linearized Navier-Stokes, and this here is the adjoint of that equation. And we can compare the chaos in both of them and have a better understanding of the forward butterfly effect, but also the adjoint butterfly effect. And in the figures that I'm showing here, we're scaling each of them by the Lyapunov exponent because they grow exponentially. Perturbations in the forward field grow exponentially. Perturbations in the adjoint grow exponentially. So we rescale them. And if we play this video, you can see the forward and the adjoint evolution rescaled. And I hope that you can notice from the video that the adjoint field is very concentrated. They're not the same. The forward field, the perturbations are filling the half channel. And if you look at the adjoint, they're much more concentrated. And if you plot the kinetic energy, you could see this here, the spread one, the blue, this is the forward chaos kinetic energy, and the adjoint field is much more concentrated in the buffer layer. You can go ahead and compute the kinetic energy budget, production, dissipation, and this is the kinetic energy, and these are the transport term. This is for the forward linearized system, and if you do it for the adjoint, again, you can see it's much more concentrated. And where it's concentrated is exactly in the buffer layer. And that's why the reconstruction from wall observations is very good below the buffer layer, deteriorates in the buffer layer, and then you get this filtering effect where you only reproduce the large scale structures in the outer flow, but not the details of the turbulence because of this chaos that takes place that is mainly generated within the buffer layer. Okay, so just to summarize, the basic question was, what is the minimum resolution? And I hope the takeaway from the talk is the Taylor microscale and the Lyapunov timescale are the two most important elements. Can we use measurements of the outer flow to reconstruct the near wall region? We've demonstrated it, and we're now trying to establish bounds on how well you can do LES wall modeling using these techniques. And if you start from the wall, can you reconstruct the flow? Well, you can reconstruct it up to the buffer layer, but then the reconstruction quality deteriorates. We outperform any algorithm out there with adjoint variational methods, but once you hit the buffer layer, you have to take a penalty in your correlation to the truth. And what is the domain of dependence? We talked about this adjoint kernel, and the spot that grows in reverse time, and the features that we can reconstruct most accurately are for a long time, or for T plus order 20, starts to become the leading POD modes. But of course, it's difficult to converge in other directions where you have weak sensitivity. So with this, I'll happily take any questions. And thank you very much.
Okay, let me thank you on behalf of everybody for a very stimulating talk. So if you have anyone has a question, if you want to raise your hand. But in the meantime, could I ask, I mean, we're talking about the energy in the adjoint solution. I mean, does it have any physical meaning whatsoever? Or it's just a way of getting information about how well you might be able to reproduce the flow in the other direction?
Okay, so the adjoint field in adjoint data assimilation, the adjoint field is the gradient of the cost function. So if you have a very large adjoint field, that means you have a very steep gradient, and the steeper the gradient, the smaller the step that you'll be able to take in your search towards the optimal. So that's one interpretation if you're thinking about the adjoint as the gradient of the cost function. In the measurement kernel, the adjoint field is essentially the cross correlation of the adjoint field gives you a sense of the Hessian. And the larger the adjoint field, the bigger the separation between your largest eigenvalue and the smallest eigenvalue. And that means it's more difficult. The Hessian is more ill-conditioned. So a larger adjoint field is a problem. I think that the adjoint field being the gradient of the cost function immediately tells you you have really steep cliffs. And that's a problem.
Yeah. Do we have more questions? Sean?
Thanks very much. Can you hear me?
Yes.
Excellent. Thank you very much for the talk, Professor Zaki. So I was wondering, when you have the forcing to the adjoint equations, presumably the adjoint velocity field is defined on your fully resolved grid, but your discrepancy measurements are defined on the grid in the measurement space. And I was wondering, how do you deal with the difference in the grids between where you know the measurements and the full grid where you're solving the forwards and adjoint Navier-Stokes equations?
So if you're, so currently we're just basically computing the measurements at the discrete locations where we have observations, or we're computing these errors at the discrete location where we have observations, and the forcing only appears at those points, but the adjoint equation is solved everywhere. So we're not using a kernel where for the errors, it's basically enforced at a point. In reality, of course, when you get measurements, they're not going to be point measurements as we do here. For example, in the work we're doing on high-speed flows, the PCB sensors for wall pressure have a finite size. So then there's a kernel for the averaging of the pressure signal when you do the PCB measurements. And then in our computation, because we're trying to reproduce the experiment, we have a region where you have average points, a collection of points over which you have the observations at every sensor. In this case, because the observation came from a DNS isolated points, we can use the same thing. But in reality, we try to model the actual probe. I hope this answered the questions.
Thanks, yes. Phil, do you mind if I ask one more question?
Yeah, go ahead.
And do any of the reference measurements, are those purely velocity, or do you also use pressure?
So for these, for volume reconstruction, we're only using velocities. For reconstruction from the wall information, sometimes we use the stresses and the pressure. But when we were talking about all this results, volume reconstruction, we're only using the velocity. We didn't assume knowledge of the pressure. In fact, the pressure is another outcome of that reconstruction, which is a nice thing to be able to do for our experimental colleagues.
Absolutely, thank you.
Sure.
Do we have more questions? Costas? I think your microphone is off, Costas.
Yes, thank you very much, Professor Zaki. Very interesting, your talk. I would like to ask if you could comment about the origin of the modes that you find. Are they reminiscent of Tolman's lifting, or there is not a relationship close to the wall?
Okay, so I think a simple way to think of it is, if you have, imagine if you have a unit energy and you want to perturb the flow to have the maximum possible shear stress. And at very short times, that perturbations might not look physical. It just looks like it says if you have a very strong span-wise roll, that will have a significant impact on the shear stress. But if you have a long time horizon, it's not very long, T plus of about anything over 10 or 20, then that energy would look like a streaky structure that basically like a roll in a streak, and that would have an impact on the sensor or the leading POD mode, because that can extract, the initial perturbation can extract energy from the background state that and would allow it to amplify and then generate a significant stress at the wall. So those directions at short time, they're less less relatable to observable quantities, but that's what the adjoint data assimilation will try to reconstruct. But at longer times, those are basically energetic structures that have a strong wall signature.
Thank you very much.
Do we have any more questions? Okay, well, let me thank Tamer again on behalf of everybody for a very stimulating talk. We'll leave the meeting room open, if that's okay with you, Tamer, for 5–10 minutes. People often ask questions afterwards rather than in the formal session.